Christos Nikolaou, that many of you still know, right? He passed away 2 years ago, and he's the co-founder of the SummerSOC, and for the last 10 years he hosted SummerSOC here in Crete, and we found a company, StartTECH Ventures, who are so kind to fund the PhD award. And as I said before, everybody may submit, right? If you have a good PhD thesis or excellent PhD thesis, right, you submit it. You need to pass in the expert reports of the PhD award, and then the PhD committee, headed by Wolfgang, asked some people of the PhD committee of SummerSOC to review the PhD thesis again. And this year we have a winner, which is not unfortunately, but a second time a German PhD thesis. It is Markus Klems for a PhD thesis called Experiment-Driven Evaluation of Cloud-Based Distributed Systems. He was advised and supervised by Stefan Thay from the Technical University of Berlin. And I read from the expert report that we asked additionally. So one citation, it has been a pleasure to read Dr. Klems' excellent dissertation, not only because it is well written, rich of ideas and interesting results, but also because of its particular high content to word ratio. That means it's written dense like plutonium. Right? So then the other stuff is the research is grounded in solving particular problems, which makes it both very timely with great potential to be immediately relevant to industry. Christos Nikolaou would have enjoyed this, right? Because he was always interested in applications. And the final quote, Dr. Klems built a tool to automate experiments and shown how to apply it to evaluate the performance of cloud distributed systems in non-trivial scenarios. Wolfgang, you need to get up. You need to pass this certificate. This certificate. Unfortunately, not get a frame. We try to get it still. So Wolfgang, you need to take a picture. He's now rich, he gets 1,500 euros. He will invite all of us at 7 o'clock. So, and now we are looking forward to his talk. Yeah? Thank you.
Thank you very much.
Thank you very much for the kind introduction. Yeah, my name is Markus Klems. I am a researcher at TU Berlin. I work in the Information Systems Engineering Group with Professor Stefan Thay. And I'm very humbled and honored to be receiving this Christos Nikolaou Memorial PhD Award. I would like to offer my sincerest gratitude for the committee for this honor, and to StartTECH Ventures for sponsoring the award. I started my scientific journey back in 2010 at the Karlsruhe Institute of Technology, KIT, and then together with Stefan Thay, I moved to Berlin in 2014 and helped to set up the Information Systems Engineering Group. I'm very thankful to both institutions, KIT and TU Berlin, and in particular to Stefan Thay for giving me the opportunity to pursue exciting research. I would also like to thank my colleagues at Karlsruhe in Berlin and other research institutions, IBM and Yahoo, with whom I had the pleasure to work together. So, in the following, I would like to present some results from my PhD work between 2010 and 2016. When I started in 2010, cloud computing was a quite new topic. It was emerging, it was gaining some traction. And I was instantly fascinated by the possibilities from a development and a system management perspective that cloud computing offers. And for me, really cloud computing is a very good example of service-oriented computing. computing principles applied to the data center. And the idea, very much pioneered by Amazon Web Services, to expose data center resources as services was quite brilliant, I think. And the continuing success of cloud computing, I think, shows this very well. So in my thesis, the focus is on methods and systems for evaluating several properties of distributed systems that run on cloud computing infrastructure. And to assess these properties, I use automation, experimental automation. So in the following, I would like to mainly show several experimental studies that I performed together with colleagues over the years, and some of the findings that we made. Then I'm going to show some methods that we developed for automating experiments, which was necessary to perform most of these experiments that I'm going to show due to the number and complexity. And then I would like to also discuss some trade-offs. So this was an idea that initially motivated my research to evaluate trade-offs between contradictory objectives that we want to achieve with distributed systems in the cloud. So I think I don't need to spend too many words on the motivation. If you want to launch a software as a service application today, if you want to start a new startup, it's highly likely that you build on a cloud computing stack, that you use infrastructure as a service, be it from Amazon, from Google, from Microsoft, from IBM. I recently read that even Deutsche Bahn is now moving parts of their infrastructure into the cloud. So for me, this is an indication that we have now reached the peak of adoption. So it's not just startup companies anymore moving to the cloud. I can remember several discussions of is the cloud secure? Can I move my data there? And it's actually quite impressive that despite concerns of data security, safe harbor, and so on, that so many companies, even in Germany, move into the cloud to build their applications and services there. So why is this the case? I think there are a couple of reasons. For once, the cloud certainly, as I said, offers a new development model. We can access infrastructure as services, which allows us to build new kinds of applications, autonomous applications that are that scale themselves, that are very fault tolerant. We can, as a developer, build our own system management tools by programmatically accessing infrastructure as a service. But more than that, the cloud services and distributed systems that we install and run on the cloud, like NoSQL databases we run on clusters, cloud compute clusters, they promise us to deliver certain objectives. In particular, the following that I've listed here: performance, scalability. Elasticity is still a term that is a bit debatable. I will explain later what I understand under elasticity. Promises you to save cost, to deliver services with high availability, and offer certain consistency guarantees, which are, however, relaxed compared to more traditional databases. There are certainly other objectives like security, but I think these are the main objectives that motivated a lot of the new systems, in particular NoSQL database systems that have been developed initially by internet companies like Amazon, like Google, and then people picked up these systems as blueprints, and we implemented it as open source software and made it available to use for our audiences. So what interested me mainly in my thesis is, do these systems, if I run a distributed system on cloud computing infrastructure, does it really deliver on these promises that I've listed? How would we find this out? So one approach could be, I ask an expert what he thinks. Should I run a Cassandra cluster on EC2 as backend for my application? And this might be a viable approach, but opinions or even of experts can be biased or can be simply wrong. Maybe they are based on experience that is outdated, or maybe it doesn't apply to the use case that I have. There are also many experiment results that are published every day on blogs or in scientific publications, which could help me in my decision-making process when I want to select a certain technology, when I'm building my technology stack. Should I build it on Amazon? Should I build it on Google Cloud? Should I use Cassandra? Should I use HBase? Should I use MongoDB? And so on. So I can look at these benchmarking results. However, as I will point out through this talk, not all the results are easily transferable, or the use cases. Then I could run my own experiments. If I don't have much time and enough budget, I could try to build a simulation model, or I could run a simple micro-benchmarking experiment that gives me some insight into the performance characteristics of a system. However, maybe a very simple experiment or a simulation that abstracts too far away from the actual complexities of a real distributed system disregards important aspects of the system. So, for example, I've seen many studies where people evaluate distributed systems without using replication. So I wonder what value these performance evaluations have if I don't use replication. It's the main reason why I would use such a system to offer high availability and horizontal scalability. Okay, then I could run a more complex system that reflects what I would see in a real production environment. And I could focus on one objective like performance. However, as I have seen and as other people suggest, many objectives are contradictory. Most famously, the CAP theorem argues that in a wide area distributed system, you can only achieve two properties at the same time, consistency, availability, and partition tolerance. So there might be trade-offs between what I can get. I can improve performance by increasing my cluster size, but then I also increase cost. I could use optimistic replication mechanisms to improve performance and maintain high availability, but then I could violate certain consistency guarantees that might be necessary for me. So it's really important to look at several objectives at the same time and not just optimize my system for performance or for just one objective. So I asked myself, how can I evaluate multiple objectives like performance, like scalability, like low cost of a cloud-based distributed system, and the approach that I took was by using systematic and automated experiments. I break this down a little bit further. So maybe we can rely to a certain degree on experiments that already exist. The question is how good is the quality of experiments that we can find out there, and am I able to reproduce the results? So a good experiment should be reproducible. So this is something that I tried, not just to point the finger at other people and say, here we discovered something that you did wrong, but also to validate my own experiments and get an idea if I'm myself on the right track. And then the second question was, because as you do some experiments, you quickly learn that you cannot do them manually. How do we automate experiments? And there are several experiment automation systems out there. We did our own implementations and gained some lessons learned from building these systems. And then how could methods look like to describe trade-off problems between conflicting objectives? Or could I even optimize a system regarding multiple objectives? How would that be? So first I would like to show some experimental studies so that you get a better idea what I was working on. And we built on related work that has been published over the years. The first publication by Cooper, YCSB, the Yahoo Cloud Serving Benchmark Tool, is a very popular benchmarking tool for assessing performance, scalability, and elasticity of NoSQL databases. And in their study, they compare different NoSQL databases, so also compare it to one relational database, regarding the performance, scalability, and elasticity. And many other people use the same tool, so this is a good foundation to compare experiment results if everybody is using the same benchmarking tool. However, it can also be a bit dangerous to only use one benchmarking tool, as we have learned through our experiments. There are certain limitations of YCSP or certain quirks that you need to be aware of. So we also ran several experiments with other benchmarking tools like JMeter or like RAIN from UC Berkeley and compared our results and looked maybe not in absolute measurements, but do we come to the same conclusions regarding performance comparisons or scalability experiments. Then there's an interesting work by Bodig, in particular for assessing performance of distributed systems under hotspot workloads. So cloud systems should not only deliver good performance for very predictable, non-challenging workloads, but they should also provide good performance for peak workloads, where we have a flash crowd that suddenly accesses our service and we double or triple our user numbers within a short period of time. And so we also implemented this statistical workload model to perform some hotspot workload experiments and compared our results to a study by Truszkowski, who also used this model to assess performance, scalability, and elasticity of they performed their study on an in-memory database. There are several extensions of YCSP. We also built our own extensions, like for implementing the statistical workload model. There's one interesting extension called YCSP++, which adds a couple of advanced features for debugging and monitoring assistance during experiments, so that you can see, for example, while your workloads are running, you can see the measurements in real time. And what they also added to YCSP, what is quite interesting, is an approach to assess consistency. Consistency itself is a quite complex topic in distributed systems. More specifically, they assess staleness of data when you have a replicated system that uses optimistic replication. Then there's a study which we looked at quite closely, because we tried to reproduce it as closely as possible for us by Rabel et al., where they assess the performance and scalability of several NoSQL databases. And here is an interesting study that looks at the performance and availability of replicated systems under certain failure scenarios using fault injection experiments, and it's quite similar to some experiments that we also do. Here are some publications that I've contributed to over the years. I will not talk about it in too much detail, because I'm going to show you some of the main results in the following. So these are 6 of the main experiments that I discussed in my thesis. The first 3, or the first 4 I will talk about in this talk. Here we have a performance experiment, and we look at how to do scalability benchmarking, how to do elasticity benchmarking. So what I want to talk about here is the results that we gained through our experiments, and also the measurement approach that we took to quantify these system objectives. Then I will also talk shortly about the more complex system setup that we evaluated using a combination of Cassandra and Hadoop. And there are 2 other experiments described in my thesis, where we assessed performance and scalability of a web application based on a NoSQL database, and an email application where we tried out different database backends and tried to compare the cost, what is more cost efficient, DynamoDB. Okay, let's talk a little bit about hotspot performance in distributed databases. In 2011, I had the opportunity to go to Yahoo Labs and work in the research team there, and together with the engineering team. And at Yahoo, they had developed a distributed database, a proprietary database named ShareHub, which has the high-level architecture as shown here. So we have several components like these routers and storage units. So the storage units store the actual data that is saved in the database. On a logical level, we have a table. The table has 600 million Yahoo users, maybe now Verizon users. I don't know what happened to the system now. But anyway, we have this huge amount of metadata, in the case of Sherpa, that we want to store somewhere. And to make it storable, because it doesn't fit on one server, we have to partition the data into so-called tablets, and these tablets are distributed on these storage units. And what was a practical problem is that under certain partitioning schemes, using a distributed order table, which enables certain types of queries for the developers, we can have patterns that lead to hotspot workloads, which means that a lot of requests are directed through the routers to a single storage unit or to a small subset of the storage units in this server cluster. And this is a quite tricky problem because we cannot solve, it leads to more volatile latency for the users, which is undesirable. And it's a bit tricky because we don't want that to happen, but we cannot solve this problem by simply provisioning more servers in the cluster. The problem is that this storage unit is overutilized, but the other storage units are underutilized. So we have a bad load balance in our system. And by just provisioning more servers, we will just have more underutilized servers. So this is the main problem that we looked at here. And the engineering team had built a data load balancer named YAK, which had the objective to resolve such hotspot situations. So whenever such a storage unit is overloaded, it should perform certain actions to balance the load in the cluster. And the way that this should happen is by redistributing tablets in the cluster in a way so that the load is more evenly balanced. YAK itself consists of several components. On the top we have this stats engine here. The stats engine collects monitoring data from the storage units. Basically the number of requests and the size of requests, or the computational complexity of the requests, or how many rows do they modify. And the stats engine sends this information down to the rules engine, and the rules engine has a couple of configurable rules, as the name suggests, and can suggest these two types of operations, move and split. Move operation means that we move a tablet from one storage unit to another storage unit, and the split operation would mean that we split a tablet, or rather this way, and then we could perform a move operation, half a tablet to another storage unit. So these are the two actions that we can perform. YAK itself does not perform these actions, but it is sent through a job tracker to this tablet controller component, which is part of Sherpa, part of the database system. And the tablet controller then performs these move and split operations. So what I looked into was, first I had to design and to model some hotspot workloads and try to see if YAK really is able to resolve hotspot situations, and also to see if Sherpa without YAK would even run into these hotspot situations. The engineering team hadn't done such systematic studies yet, so I came there to evaluate how YAK performs. And what you can see here is one example that shows that YAK does indeed improve load balance in a cluster. We have this dotted line, which shows an experiment run where I disabled YAK, or I run YAK in so-called recommendation mode. So the load balancer would suggest some rules, would say, okay, do a split operation or do a move operation, but it wouldn't actually send these commands to the tablet controller. And then I reran the experiments using the load balancer in execution mode, so that the tablet controller would actually execute these commands. And what you can see here, the dotted line shows that the storage unit heat, which is a server-side kind of artificial metric that is computed, that is collected through the stats engine to assess the load that is caused by a user workload on a storage unit. You can see that the storage unit heat is increasing if we don't perform these load balancing actions. If we perform load balancing actions, moving tablets in and out of storage units, then we can see that we can maintain a much flatter line here, so the storage units don't heat up so much. However, I could also see that there are quite significant load spikes whenever we move the tablet out or when we move the tablet in. So this series of, and you can see that increasing storage unit heat on the client side also reflects the increasing volatility of latency on the client side. So this helped to refine certain rules of the rules engine of YAC and thereby improve these data load balancing algorithms. Okay, next I would like to present some results from scalability benchmarking experiments that we ran for evaluating the scalability of two NoSQL databases, Cassandra and HBase. And we thought of several benchmarking measurement approaches, loosely based on the Wisconsin benchmark for parallel databases. So the first approach would be to run a workload and then increase the workload by keeping the capacity the same, kind of running a stress test on our system. Another approach would be to run a workload and increase the capacity and see if we can maybe improve latency. And the third approach, the one that we really did, was to run workloads, increase the workloads, and also increase the capacity in proportion to the workloads to see if our system scales linearly. We did several experiments, and in one major experiment we tried to reproduce the results from Rabel et al., which they had published previously, and they had given us a very accurate, a very detailed description of the workloads they used, of the system setups that they used. They evaluated NoSQL databases in a particular application context for application performance management. So we need a database to store performance monitoring data of applications, so there are a lot of write operations. And there are also a couple of read operations for administrators or system managers to view the performance of the system. So you have a lot of write operations, and you have also several range queries, several read operations. And what they found out is Cassandra is the winner, a clear winner in terms of throughput. HBase is also pretty good, has lower write latency, however higher read latency than Cassandra, and both scale linearly within the experiment setup that they did their experiments on. And so we tried to reproduce the setup as closely as possible. One challenge was that this was related work was run on physical infrastructure, which we did not have access to. We tried to reproduce it in cloud-based infrastructure. And this already presented some challenges for us to find a good fit of virtual machines in the Amazon Elastic Compute Cloud that reproduced this physical setup. And we got it wrong a couple of times until we could reproduce the results to a certain degree. In the end, we could maybe confirm the results. HBase and Cassandra do scale linearly in the range of servers that we tested, between 4 to 12 servers. Cassandra performs better for read-heavy workloads, and HBase performs better for write-heavy workloads. For Cassandra, for setups on Amazon EC2, we also found out that there is Cassandra is more CPU bound than HBase, so we ran here into a CPU bottleneck, setting up our initial experiments, and then had to rerun them a couple of times until we could achieve similar performance measurements as in the related work. In one instance, we also found out that for HBase, we could achieve much better performance than in this related study. And the reason is that we observed in preliminary experiments that there was a client-side bottleneck, So we increased the number of benchmarking clients to resolve this bottleneck, and then we could achieve much higher performance. So previously we ran in the same bottleneck that you could see in the data from the study that we tried to reproduce, and so we basically reproduced that bottleneck. And but we saw that we need to increase the number of clients because we're not assessing the performance of the system, but we're assessing the performance of our benchmarking clients. Then we extended these experiments to assess elasticity of Cassandra and HBase. And for that we devised, or we thought of two measurement approaches. The first, so what we are interested in when we are measuring elasticity is the behavior of the system during a scaling action. In particular, does scaling impact the user workloads that are running on a system, and how quickly can I scale? So performance stability and the speed of scaling are the main characteristics that for us determine elasticity of the system. If you can scale quickly without impacting user workloads, then it would be an elastically scalable system. If this is not the case, then it would be less elastic. And we thought of, okay, we can do this in two ways. Either we manually execute scaling actions, we add a new server, we horizontally scale our system, and we encode this into our experiment plan. So we know exactly when the scaling action happens and when it ends. Or we could use a framework that does auto scaling, like Amazon auto scaling groups with the corresponding policies, CloudWatch metrics, and so on. But to more easily explain and interpret the results, we decided to use this first approach. So specify in our experiment plan when we are scaling. So we ran a couple of experiments, here shown with the Cassandra cluster. We have a cluster with 3 nodes. It stores 30 gigabytes, and then we are adding a server. We're adding 3 servers, and we are vertically scaling and increasing the capacity of a single server. And what we could see here, and this was somewhat expected, but now we could also quantify it, is that we have a trade-off between the speed of scaling and the performance impact that the scaling action has on our user workloads. The reason is that whenever you add a new server to your database cluster, you have to repartition the data and stream data to other servers. So you're using up bandwidth within the cluster, which is then not available for the user certain workloads. And we reran these experiments with different configurations. So streaming refers to a configuration in our cluster. How much streaming bandwidth do we allow as a maximum our cluster to use for these scaling operations? So if we throttle it down to 5 megabit per second, then scaling takes very, very long. But our average read latency is also the lowest. This also applies for write latency and also for upper percentiles. If we give it a bit more bandwidth, then we can scale more quickly, but we can see that it has a certain impact on our user-facing workloads. Latency increases, and if we run it as quickly as possible, then we can scale it, in this case, in 16 minutes, in this case, even in 13 minutes, because we can distribute the load to multiple servers at the same time, but it has a more significant user impact. We can also disable streaming as suggested in a related work, and then scaling works very quickly because we don't redistribute the data. And it also doesn't have much impact on the user-facing workloads, but this has some drawbacks, which is due to the technical details of Cassandra. If we are disabling data streaming, then we are basically using the new nodes as a caching layer in Cassandra. So it's not really recommended to do this or only for certain workloads. So we also did some experiments with a multi-cluster setup where we use Cassandra in combination with Hadoop. And what our idea here was is can we rebuild kind of a data warehousing system where we have an application database that receives some application workloads. So it's kind of like a transaction processing system. We don't have transactions here, but simple read-write operations, something like this. And then we replicate the data somewhere, so this is a logical setup, and do an ETL processing step into a query database from which we then, on which we then perform data analytics. So this was at the time when we didn't have Apache Spark and things like that, Apache Flink or Spark. So we try to do it with Cassandra and MapReduce jobs. So this is one exemplary system setup on which we performed our experiments. Here we have two YCSB clients which coordinate with one another through a coordination system, Zookeeper, and then run workloads on our Cassandra cluster. And here we have another workload generator which runs MapReduce jobs on our Cassandra cluster, which is a replicated cluster of this one, where we have an overlay that allows us to run MapReduce jobs. And we tested different setups, so maybe we could run everything on a single cluster. So we have our application workloads, our Cassandra workloads, and we have our MapReduce workloads on the same cluster, but this turned out to, this is a bad idea because the MapReduce jobs very much affect our application serving workloads. So then we tried out these different dual cluster setups, and we also tried out different replication techniques. So the data from this application cluster is replicated over here, and then on the replicated data we perform our MapReduce ETL style jobs, and then we can query our data in this cluster on the right hand side. So we ran a couple of experiments again with Cassandra alone and with the MapReduce jobs, and we could see that in any case we have a certain overhead imposed through the MapReduce jobs. Here's a single workload trace where you can see this quite significantly. And we found out that a dual cluster setup where we use asynchronous replication is probably the recommended setup if you want to combine these two systems. Okay, so we ran a lot of experiments. Could find out certain properties, how do databases that are used by Netflix, by many other companies, Deutsche Telekom, how do they behave under certain workloads, under certain, we also tested certain failure scenarios, how do they scale, is it linear, what is the performance overhead of scaling, and so on. And for performing these kinds of experiments, we had to build experiment automation tools. Because very early on, we experienced that, okay, the distributed systems, to set them up is very complex, it's a very error-prone process. And it's also very difficult to collaborate with anyone to repeat and reproduce experiments. And certainly for several experiments like testing scalability or doing these preliminary tests where we check out different instance types, where we test different storage devices, and also where we test different system configurations, system replication settings, clustering settings, and so on. It requires a large number of experiments. And we also don't want to do it just for one type of workload, but we want to do it for different types of workloads. So maybe a read-intensive workload, a write-intensive workload, read, modify, write, and so on. So for this purpose, we developed Elastic Lab, which is our experiment automation system for running experiments with distributed systems on public cloud infrastructure. And it's actually on a high level very simple. We have in the middle this experiment controller, and the controller sends commands to an infrastructure controller, software controller, benchmarking controller, and this measurement controller. And our experimenter can communicate with this heart of the system through a cloud interface. So how would a process look like? Our infrastructure controller provisions infrastructure in the cloud. So we provision EC2 instances, we set up the firewalls properly, we mount block storage devices, and then we distribute software on our EC2 instances. And the next step, and this is maybe the most challenging one, is to install and configure the software properly. So once we have distributed our software packages with HBase, with Cassandra, we need to set it up so that it connects into a cluster. And during this software distribution and install process, we also need to distribute benchmarking clients and also monitoring agents to get client-side and server-side measurements of the system when we execute workloads. So this is not necessarily running on the same cluster, but we have maybe two different clusters for the benchmarking clients and for our system under test. Then we start the services. We start first our monitoring agents, and then we run workloads. When the workloads have finished, we collect the data from our monitoring agents. Maybe they have sent it to a monitoring master, and also collect the data from our multiple benchmarking clients. And we store it in a persistent data store, such as Amazon S3, so that then we can terminate these servers and we can run our next experiment, the next workload, without having to fear that we have some side effects. So we could also reuse this infrastructure, but since we are performing certain operations on a database, it would probably cause side effects, like if you do a lot of update operations, a lot of data would materialize on the disk and potentially slow down the database. There are other experimental automation systems that have been developed over the years, in particular in the context of the grid computing community. So we have tools like Expo, we have tools like Weevil, which do similar things, however in a different infrastructure context. And two tools that are also running on cloud infrastructure, performing experiments on cloud infrastructure, are Wave and CloudBench. CloudBench is developed by IBM Research, and they share certain similarities and have also some differences to the approaches that we took for our systems. So maybe one of the biggest differences to CloudBench, which is otherwise a very nice tool, is that they hard code the system under test as virtual appliances. So they require a lot of setup work to be performed by the experimenter, which I think is the main weakness of CloudBench. We can compare the systems with regard to the experiment client, so whether or not to use an interactive command line interface. Some tools implement this. We also did this in the first implementation of ElasticLab. This facilitates explorative experiments, so you can get quick feedback. However, if you want to derive statistical models, it's often a better idea to run planned experiments that are based on an experiment plan, like a factorial design. And for this purpose, we developed here this user interface that allows the experimenter to select certain configurations for an experiment. And Wave and CloudBench also have certain support for planned experiments. And we implemented this as an extension of the first implementation, ElasticLab, and then of our re-implementation where we used Ruby. Another implementation of our experimental automation system that we implemented is as a plugin for Jenkins continuous integration server, where you can run experiments, performance and scalability experiments as jobs in the Jenkins server. So this allows kind of continuous experimentation. Whenever you have a big release, you can run these experiments to assess performance properties, to assess scalability properties of the system. Then another design decision that you can make, or that we found in the literature and that we came up with ourselves, is either to do a script-based software automation approach, basically writing shell scripts and executing these through kind of a remote execution framework, which is an approach that these grid computing frameworks use, and also in my first implementation wrote a couple of scripts to perform the setup of my experiment environment. However, this imperative approach has certain drawbacks, because it's not really so reliable for planned experiments where I want to test many different configurations of my system, because by performing a command using scripts, I never really know where I end up. So it's a bit related to problems by earlier configuration management. Another approach that I have only seen with cloud benches is virtual appliance-based approach. I criticize it a little bit. I think that, however, with container-based systems like Docker containers, this approach should be revisited and maybe becomes a bit more applicable as it is more lightweight now to exchange configurations through containers than it was previously using virtual machines. The approach that I took with the beta implementations of Elastic Lab is to base it on configuration management solutions, in particular Chef, which we used and which allowed us to build declarative experiment plans that allow us to specify the state that we want to achieve with our experiment rather than the steps that lead to a certain experiment result. Okay, then we used these experiments to assess different properties of distributed systems on cloud computing infrastructure. And one challenge that initially motivated me to go into this direction was the CAP theorem proposed by Eric Buer in 2000. He says that in a wide area distributed system, we have these three desirable properties, of course other properties, but these are special because, as he said, you can only achieve two of these properties at the same time. So you can have a wide area distributed system, which is available and consistent, but then it doesn't tolerate network partitions that can happen between data centers. So if you replicate across data centers, it can be available and consistent, but then you won't be able to tolerate network partitions. You can tolerate network partitions and be consistent, but then you would need to reduce availability. So in the case of network partitions, you would basically not allow users to perform certain operations. And you can be partition tolerant and you can be available, but then you have to drop consistency, strong consistency. So you can allow in such a split brain situation to update data in different parts, different partitions of your system, but then the data becomes inconsistent in between the partitions of the system. So there were some people who thought a bit more about this problem, like Mr. Abadi, who introduced performance into the game. So we don't only have a trade-off between availability, consistency, and partition tolerance, but if we think about performance, then we also have a trade-off between availability, consistency, and performance. So in the case that we don't have these network partitions, there's another trade-off, performance-related. So I asked myself, can I somehow characterize these trade-offs in more detail? Can I give maybe a quantitative assessment? If you want more availability, you have to give up a little bit consistency. Can I somehow put a number on these things? And I looked into different frameworks that I can build upon, and one framework that I found is this architecture trade-off analysis model published a couple of years ago by CMU, where you go through these phases of requirements, and scenario requirements gathering, then developing architectural views, model building, and then a trade-off analysis. An interesting part for me was really here. What they proposed is through qualitative analysis, some stakeholders come together, describe the architecture, and identify components in the architecture which multiple qualities are sensitive to. So maybe I have a component in my architecture that influences performance and that also influences security. And if I have such a component, they call it the sensitivity point. And if the attributes, if I make a configuration of this component, I use a different cryptographic algorithm, and it improves security, but it reduces performance, and they call this attribute of So I suggested to supplement this model using not just subjective input from the stakeholders that come together in this qualitative process, but to enrich this process through systematic automated experiments. So in the second phase, you would create an experiment plan and also create the experiment artifacts that you need to perform experiments, like create workload models, specify configuration files to provision the system under test. And then in this phase we would conduct our experiments and review the results that we get, build statistical models, and then we can identify, describe, and refine these trade-offs. There are different stakeholders involved in these different steps. We have an experimenter who is involved in nearly all the steps to prepare and execute the experiments. And we have a decision analyst who is involved in modeling and analyzing trade-offs. And then we have a decision maker who provides subjective preference information. He says, okay, given the information that I see, I prefer performance over cost, or the other way around. I implemented this general model into two instantiations that you can see here. The first method, the purpose of the first method is to describe a trade-off problem statement in more detail. So we can take something like the CAP trade-off, run experiments, and learn more about the trade-off problem. And then we see, okay, there's a trade-off between not just consistency, availability, partition tolerance, but also a performance trade-off. And if we look into performance, then we have a throughput latency trade-off. So you can make this more fine granular to better understand the trade-offs for a specific system. With the second method I attempted to allow people also to optimize or to find an optimal solution based on objective experiment-based data and subjective preference information. And the way that this basically works is we design our experiment, for example, using a face-centered composite design, as shown here. We can then, through the experiments that we run, we can get data to model, like here, a regression, a response surface model. And then I run this approximation. I use it in a multi-objective optimization problem. So I use this as an input. Here you can see, for example, throughput depending on replication factor and the number of servers. So I have a functional expression that I can then use in this optimization model, and I have this for throughput, I have this for latency, I have it for consistency measurements that I make. And then I solve this multi-objective optimization problem in an iterative fashion. So I need some initial data, some initial thresholds, like I want this minimum throughput, I want this maximum latency, I want this maximum cost. And then I see if I can solve this problem, and it will give me some point with certain values, and I show these values to the decision maker. And I can also show to the decision maker if I give up a little bit of this objective, which is maxed out, I can gain a little bit of this other objective. So this was the main idea, to have an iterative process, which iteratively includes a decision maker, gives them some information as a basis for decision making, and then plays this back. Okay, I'm already at the conclusion of my talk. So what did I do mainly in the work that concludes in my thesis? I tried to reproduce several rather complex experiments. I tried to learn from these experiments, validate my own experimental results, and also validate the results that others have produced. And in this process, I developed several systems and approaches to perform measurements of properties like scalability, like elasticity, and also suggest certain design principles for building experimental automation systems, because of course I have built some prototypes. They're probably not very usable to other people, but I also try to derive some design principles. What design decisions can you make when you build an experimental automation system? What are the advantages, what are disadvantages. And last but not least, so this was my initial goal. I only achieved it to a certain degree. Can I find methods? Can I come up with approaches, with tools to characterize trade-off problems between conflicting objectives of systems in more detail than the existing state-of-the-art allows us to do? And here I came up with two methods, one to describe trade-off problems, and the other to run this optimization method on approximations gained through automated experiments. I'm not sure how I'm in the time, but...
On the very minute.
Okay, thank you very much.
Thank you. Hagen, the Zuschauer.
Yeah, thank you for the great talk. I also love that it starts with reproducing experiments of others. We do that much too rarely in computer science. I have a quite specific question, which comes to my mind since I first started to talk about benchmarking systems, and it's regarding elasticity. So if I understood correctly, you put the system in a reconfiguration mode while you keep the workload and see how the performance gets worse while the system is busy with doing something else.
For certain experiments, like the elasticity experiment.
Yeah. This is the type of experiment. So this benchmark, is it a synchronous or an asynchronous benchmark? So when it sends a message, a query, does it wait for the answer or before it sends the next one, or does it keep sending them with a defined frequency?
So this is one configuration of many configurations of the system that you in some systems can make on the client side, and in some systems you can make it on the server side. For example, with Cassandra, with which I made many experiments, you can specify this on the client side. There's a configuration consistency level parameter that basically specifies, given a certain replication factor, so you have a number of, for example, n replica in your system, how many of these replica should be involved in a synchronous request. So, for example, I have a replication factor of 3 in my database system, and in my client, I can specify this for read and for write requests. I can say for a read request, I want to ask 2 replicas synchronously.
I think my question was a little bit different. It's about the measurement.
Oh, the measurement, okay.
So if I measure latency, it's different than if I just send asynchronous messages out and measure when they come back, or if I just wait for the completion, because otherwise they will buffer up, or they will not buffer up at the server side, right? That's
true. I think my answer is nevertheless somehow related. I get what you are pointing at. We didn't look at that. I mean, in the end, I would argue that it is something that we specify as a configuration of our benchmarking client, and we look at several server-side measurements as well to also assess and also compare from a client perspective. I mean, at a certain point, at least if we have a long-running experiment, if requests buffer up, I would see this on the server side, and then I can conclude from that that I have a problem. But it's quite tricky.
Yeah. Thank you.
Morgan.
And what is the relationship with other approaches like PBC for databases?
Well, that's also a very well-established benchmark, however targeted at relational database systems. And I focus more on NoSQL databases, specifically to evaluate replication mechanisms, and so I didn't look so much into relational database systems.
Are the tests available? So my question is, can I just download it, take my database and test my database?
To be honest, it's a prototype and it's not so easy to set up and to use.
So you speak about replicability?
Yeah. To be completely honest, I mean, it's very difficult to build these kinds of systems, and I mean, the distributed systems themselves are complex and they are rapidly evolving.